at the University of Hamburg, and he's been in Australia now mostly since 2018 at the University of Queensland in Brisbane, and also at the same time partly in part-time associate professorship at the University of Tromsø in Norway. So I'm very happy to have Martin here from that far away. He came especially for us for our 2-hour workshop. He's here in Germany at the time anyway. But yeah, I'm very, very happy that you're here, Martin. Welcome.
Yeah, thank you very much for the kind introduction. Hello, everybody. Hi. So yeah, today we'll basically do a workshop on tree-based methods, right? So before we start, I'd like you to basically access or have access to the materials. It would be great if you could just Google my name plus GitHub. I'll do the same here just so that you can follow. And if you do that, you will come to a GitHub repository, right? Click on that. And once you're there, you need to go to repositories. And there you'll see Trees U Bonn for Trees workshop at the University of Bonn. And there you have all the materials and everything we're going to need. And because this looks really weird, just click on this link here. You see this? Yeah, if you click on that, you'll actually get to a website where I have everything stored for today. All right. Cool. All right. So yeah, most of what I'm going to talk about is just an adaptation of an already existing tutorial that I wrote for the Language Technology and Data Analysis Lab, the LADAL, that I'm running in Brisbane at my home university in Queensland. So if you want to know more or explore other things that you can do with R or statistical methods, feel free to visit the LADAL website, right? You'll find lots of stuff there. About myself, Svenja already said, well, I do linguistics. I'm computational quantitative corpus linguist, which means that I look at language empirically, meaning I analyze data and then try to find out basically, are there certain patterns, right? And most of the time, what I do is I try to basically investigate certain phenomena and then see what factors impact that phenomenon, right? So for example, in American English, you might have heard it, there's this kind of thing that's called like. And for example, you might say, he's like stupid, right? Or things like that, right? So you have this like there, and you might be interested in finding out, okay, what factors impact whether someone uses like or not, right? And so if you're looking at a certain phenomenon and you want to analyze what factors impact or lead to the use of a certain phenomenon, then you can use statistical methods to basically find out what factors have an impact on the use of it. Right? So that's most of what I do. Now, in addition to being a lecturer in applied linguistics at the University of Queensland, I'm also part-time associate professor in Tromsø. And I'm also associated with 2 different labs, namely the Aqua Aurora Lab in Tromsø and the LADAL in Brisbane. And I'm also CI of 2 third-party funded projects, right? And basically my role is to help people use computers to analyze language, right? So yeah, today we'll look at a statistical method. If you have any questions or if something doesn't work, please let me know, right? Because typically when you have a problem, other people will have the problem as well. And really, if you have any questions, if anything is unclear, just feel free to say so, right? Okay, now just in terms of what I plan to do in this workshop is that first we'll basically start with the setup and have an introduction about what we're going to learn, right? And I'll tell you a little bit about the project, then about the workshop. Then we're going to delve into basically tree-based methods. How do they work? Why do you use them? What are their advantages, the disadvantages? Then we'll have a practice session where we really try to work with data. And then, yeah, we'll have an outro. So just, saying goodbye, packing our computers. And all right, so that's basically in terms of the introduction. Just to give a feel for where you're at. Who of you has ever used statistics when analyzing language? Yeah. So a few people have used statistics, some of you don't, right? which is perfectly fine. Now, whenever you have a question, when something is unclear, when you don't understand a word or something, just let me know, right? I'm really happy to explain stuff. Might not be the best explainer, but I'm giving my best.
Yes.
Yeah, sure. All right. Okay, so what we need for this workshop is really just this website. Has it worked for you? Have you access to that website? Yeah. And then all the materials are on that GitHub repo, which looks weird. Like GitHub allows you to upload stuff on the web and everybody around the world can access it, right? And also what I'm going to present today will just stay there. So basically, if you have questions later, you can just check it out. Everything I'm going to talk about will be there and you can use it whenever you want, right? Okay, then for the last part of today's workshop, there's this practice part here. And there we're going to use data ourselves, and we're going to use virtual machine. And in order to start virtual machine, just need to click on Launch Binder, but you don't need to do that now. You can do it now. You don't have to do it now. I would actually suggest that we wait a little bit. All right. Everybody eager to learn about tree-based methods? Yeah. Okay. So, so some of you have used statistics in their work, right? Typically, what I said is when we're using statistics, we want to find out something about relationships, right? So all of quantitative or all of inferential statistics, all of quantitative analyses, mostly what they're concerned with is to find out about relationships between them, right? So we want to find out how does X affect Y, right? Why do we do stuff? And quantitative linguistics looks at measurable relationships between them. So whether something has just a random impact or something, so whether there's no real effect or whether you can really use this. If this is the case, then probably that will happen, right? So that's mostly what I do. I try to figure out relationships between things. And tree-based methods are actually quite nice. And what they do is they basically split the data up. So imagine you have 1,000 people chosen at random, right? So you have a group of 1,000 people, just you collect them from the street. So you have a whole bunch of people, right? And now, basically, you want to find out whether they're men or women, right? And so what factors, what variables can you use to basically determine whether they're male or female? You're not allowed to ask them that question, right? So you have to use some sort of predictors for that, right? What could you do to basically determine whether they're men or women? Color of clothes. So how would you go that? Would you say light and dark, or how would you operationalize that? Right. So color of clothes could be one variable, right? What else could you use? I'm not asking you to give me the perfect predictor, right? I'm just asking you if you had different variables that you could assess, right? What could you use to determine that? Yeah. Right. Do you have facial hair or not? Right. You can basically inspect that. That'd be a great predictor. Other things. Right. Very difficult, but yes, you could do that, right? What else? Height. Height would be a very good predictor, right? Again, not perfect, right? What else? What else could you use? So facial hair, pitch, height, darkness of clothes. Yeah.
Stereotypes for male and
Yeah.
female. Things like clothes or dresses and skirts, usually stereotypically female, and
Right.
categorize that length of hair.
Yeah.
Also, in stereotypes, women have long hair. Of course, it's still not true in itself, but
Yeah, I get that, right? Yeah.
Jewelry.
Yeah.
Usually women wear jewelry.
Right. Makeup. Right. And none of these predictors are probably perfect, right? But imagine it like this. You just basically want to, first, you'd probably take age, right? And everyone above, let's say 170 would go into the male category and lower in the female category. Now, these two groups, they would not be perfect, right? You would still have a high percentage of women who would be above 170, right? And you'd have lots of men who are smaller than 170 that would be in that category. But you'd have basically not 50-50 in each category, right? And so what a tree does, it basically takes variables and then splits the data. So the first split here would be height, right? And then, for example, you could try to take, does the person have facial hair, right? And then another split, right? And then among, for example, the people who do not wear dress, who are below 170, you would ask for a facial hair, right? And you make another split, right? And so in the end, what you want to have, as clear distributions as possible, right? That's essentially what those trees do. And I just want to show you what the tree looks like. I think I have it. What online, what you don't see is that you're in front of where I need to go at the moment. Yeah. This is something that we'll deal with later on, right? So here, this is what a conditional inference tree looks like, right? So it's basically like a tree structure in the sense that you have branches, right? And then at the bottom, you have, these are so-called nodes, right? Which are the final distribution of things, right? And in this example that we're going to go over later on, we're interested in whether a person uses discourse like the one I talked about, right, before, or not, right? And what you see here is that the most important or the best predictor would be age. And it separates between young people and old people, right? And then among young people, another factor would be socioeconomic status, right? And then basically, if you have high socioeconomic status, then you have people have a very high probability of using one, right? Whereas, for example, if you look at the old people and the male old people, they have a very low probability of people using light, right? So dark is, yes, they use light, and light is they don't use light, right? So in the end, you basically want to have the nodes, you want them to be as distinct as possible, right? It doesn't work when we're dealing with messy data. But for example, if we know that someone is young and high socioeconomic status, we know that the probability of using light is much higher compared to an old speaker who is male, right? So we want to have, basically want to separate the data, want to partition it up to have maximally distinct distributions, right? Okay. Now, when I just go back here, this would be that tree if we basically applied all the variables that are available to us, right? So here we have age, most important predictor for using discourse like. Young would go here, old would go here, right? So yes, it's always to the left, right? So age 15 to 40, yes, right? Status high, yes, then go here. Gender, female, yes. Will that person be a light user? Yes, it will be a light user, right? Is that person 15 to 40? No. Is the gender female? No. Is the status high? No. Then it will not be a light user, for example, right? So this is just our best guess of dealing with it. But this is how you can understand these kind of conditional inference trees, how they're displayed, right? Now, why do we use conditional inference trees? So we use them because when you use statistics, many of the statistical tests that are taught to you at the university, they are bivariate, which means that you only have two variables that you look at, right? You look, for example, at gender and the use of discourse markers, and then you only look at the two, but you ignore all others, right? And then you look at age and discourse like, and you ignore all other factors. Now, one advantage here is that you look at all the different variables at the same time, right? So you can basically take into account what happens if we control for the effect of other variables, right? Right. Now, as you saw before in that picture, it's really not perfect. You don't arrive at perfect predictions, but you have a better than chance probability of getting it right. Yeah. No, that was basically the data set consists out of people who are 15 up to 40, right? And then 41 to 80, right? So you can be either young, right, or old, right? And if you're 41, you count as old, right? So it's just basically, I'm 42, so I'm less. So really, it's just the way that you measure something has an impact on how it will be displayed in the tree, right? Yeah, yes. So it depends. I'll give you an example in a little bit, right? So let's say you have, you look at what people wear, right? And you could say dark or light or colorful and not colorful. So when you, for example, have coded colorful and not colorful, then that can be a split, right? But if you've coded something else, right, then you basically, it can only split by things it knows, right? If you don't enter it, right, it won't be able to split on that, right? Yeah.
Does it need to be a binary?
No.
So have more binary.
Yes. So the great thing about that is that it takes all types of predictors and all types of dependent variables, right? So it's not only yes, no. You can also have numbers like -50 to +50, right? It can take binary, like yes, no. It can take nationalities. It can take genres, for example, right? So the great thing about this is that it takes all types of predictor variables and all types of dependent variables, right? So it's super flexible, and that's a great thing, right? Whereas if you have a chi-square test, it only takes counts, right? So it doesn't take any other variables, right? And this method is, yeah, it's super flexible. That's a nice thing. That's one of the reasons why I think it has become so popular, right? Just to give you an idea, basically it was first introduced in linguistics in 2012. And ever since then, you really have a clear growth curve and people who use it, right? So it's very easy to use, right? It's quite intuitive. Like even if you do not know statistics, you can interpret this tree, right? More or less, yeah? But basically, what you have here is basically best guesses, right? For how to classify a certain language user, right? Or you have something like the probabilities, if you have the bars that we looked at earlier, right? Okay. Now, I already talked about an advantage of this method, which is that it takes all types of variables, and that also it's multivariate, which means that it takes as many variables as you want to put into it, right? And for each variable, it basically tests how good is that variable to differentiate between different speakers, right? And you have these decision trees, which will basically split by all variables that you give it, right? And then you have something that we have here, which is called a conditional inference tree, which only splits if there's a significant difference, right? So the difference here is that it splits only if there's a significant difference, right? So for the young speakers, there's gender is irrelevant. So there's no statistically significant difference here for gender, which is why there's no gender split, right? That's called a conditional inference tree when we have something like that. In contrast, here it will split by gender even if there is no significant difference. We'll just basically use all the variables that you give it, right? And we'll always split when it can, right? So that's called a decision tree, right? So decision tree will give you all possible splits, and conditional inference tree will only give you those splits where there's a significant difference, right? Okay, very good. Now there's certain problems with these types of models. So one problem is that here you see that there's a split by age, right? Now, that means that age really has an effect by itself, right? So there's a difference between young and old speakers, right? But sometimes you have things where you have no clear main effect of something, but you have something that's called an interaction. An interaction is, for example, imagine you really hate coffee. You don't like coffee, right? But when you have a cigarette, then you love coffee, right? So that means, yes. But it means that here, your liking of coffee depends on something else, right? So just when you ask, do you like coffee, right? You can't say yes or no, right? Because it depends on whether there's a smoke or not, right? And this assumes that there's always a clear split, a yes or no, right? Do you like coffee? Yes. If yes, then go right. If not, go left, right? But if you have an answer that's it depends, then there's a problem, right? So that's one of the disadvantages of these tree-based models, right? And if you have data like that, then another method, which is called a regression, would be better. But regressions are much, much more difficult to implement. Of course, there's much more that can go wrong, right? With conditional inference trees, they're super easy, they're easy to use, they're easy to interpret, they're super flexible, it's all great. But if the first factor, the most important factor, is this kind of conditional thing, then actually they don't perform well. They might actually give you wrong results. That's just something that you need to know. Yeah. It depends on your dependent variable, right? So here we use one type of model for all types of dependent variables. When you use regression, you use different types of regression depending on your dependent variable, right? So if your dependent variable, that what you're interested in is yes, no, then you use a logistic regression, right? If your dependent variable is, for example, certain frequencies or something, then you use a linear regression, right? And if you're dealing with counts, like how often something occurs, then you're actually dealing with a Poisson regression. So there, the type of regression, type of model depends on what you're interested in, how it is measured. For this model, it doesn't matter, right? You use exactly the same code, the same method. That's it, all right? Okay. Now, there's another thing why conditional inference trees aren't that great, and that's called overfitting. Just a moment. Overfitting means that when you take a data set and then you apply this method and you have this nice tree, right, that it works very well. It's the best tree for your data, right? So given the data, you'll have the best possible split, right? But if you have other samples, like if you would collect the same data again, then probably the tree wouldn't be optimal for the new data. That's called, it's overfitted to the data that you use it for, right? And that's a problem. You have other methods that basically solve the problem of overfitting, and they would be extensions of this model. These extensions would be called random forests or Baruta. They're also tree-based methods, but they're more advanced. Basically, what they do is they don't just create one tree for data, but they create many different trees for the data, right? And when there are many different trees, that's why you call it a forest, right? Now, we will not deal with random forest here. I'm just going to teach you this method, right? And you just need to be aware that there can be problems with it. So one is if you have the most important factor is conditional, and that's only for the very first split. All other splits, they can be dependent. That's not a problem, right? It's only the very first one, right? All right. And they overfit to the data, which means that they really give you an idea of the data at hand, but they're not super great at being applied to other data sets. Okay, so that's what I wanted to tell you essentially about this. Now, the next thing is, how do these methods work, right? Now here, the first example that we're going to use is we're going to look at whether people use discourse like, right? And we have age, which is either 50 to 40 or 41 to 80. Gender, we just use binary here for simplicity, and we have status, which is no and high, right? So all the variables in this data set are just binary, right? And we use it because it's very simple. It's a very simple data set. I didn't want to use a very complex data set, right? Now, the question is, what should be the first split? We already know it's age, right? But how do we know it should be age, right? It could be something else, right? For example, with the people that we want to classify, right? We don't know whether height would be the best split, right? It could be something else. Could be facial hair. It could be skirt. Could be makeup. Could be all sorts of other predictors, right? So how do we know what method works best? So where should we split first, right? By the way, on the internet, just could you give me feedback whether you understand me or not?
Yes, we
Yeah.
understand you.
All right. Also, we're recording this. And so you don't only have the materials available, you'll also have access to the recording. So you can actually watch it if you like. Okay. Now, in order to split the data, to find out what the best split is, how that works is you basically tabulate the predictions. So here you have female and male, and no for the person doesn't use like, and yes, the person uses like, right? Then you have age, you have young and old, and not a like user and like user, right? And down here we have status. So we have high status and low status, and not a like user and a like user, right? So the first step is to tabulate the just the occurrence, the frequency of how often does this combination occur, right? And then in the second step, we calculate the so-called impurity measure, which is also called the Genie coefficient. And the Genie coefficient tells you how different the distributions are, right? So if we split by age, then we'll have maximally different distributions, right? What do I mean by distribution? Let me just open Paint and draw something really quick. Because I use this word a lot, and probably it's difficult for you if you're not dealing with distributions often. So imagine you have a coordinate system, right? And then you might have, let's say this is like users, yes, and this is no. Maximally distinct would be if you have, or well, not maximally distinct, but a very distinct pattern would be if there's a big difference between the number of like users and non-like users, right? So that would be very distinct. There's a big difference. If you don't have a big difference, like if the yes like users would be like this, right? What this would mean is that you basically calculate what the Gini coefficient is for a distribution that looks like this, where there's almost no difference, or for a distribution where there's a big difference, right? And what we want to have is we want to have a low Gini coefficient. So the lower, the more distinct the distribution is, right? Okay, so the way that it works is, remember we have the numbers here, right? So for males, it would be 42 like users and 75 not like users, right? So to calculate the Gini coefficient for the man, we would take 42 divided by 42 plus 75 squared minus 75, not the like users, divided by 42 plus 75 squared. And that would give you 0.46, right? Don't worry about it, you don't need to do this, right? I just want to explain how it works, like how we arrive at that split. You don't need to do this, right? But I need to explain to you, like, how does the computer decide what split comes first, right? That's why we're doing this, right? Okay, and when we do the same thing for the women, we have 43 women who do not use like, and 91 who use like, right? And so if we apply the same formula, we get a Gini coefficient of 0.43, right? Now you have a problem because we don't have the same number of males and females, right? So if you want to have not the Gini coefficient for males or for females, but for gender, we can't just say female plus male, but we need to take into account how frequent are there male, how frequent are there females, right? And in order to do that, we take the number of man divided by the number of totals times the Gini coefficient for man, and then plus the number of women divided by all people in the data times the Gini for women. And if we do that, we get a Gini coefficient now for gender, right? So what we did is we first calculated Gini for a man, then we calculated it for women, and now we take the frequency into account and get a Gini coefficient for gender, right? Okay. Yeah. No, it's still for yes and no, but yes and no when we take the frequency of men and women into account, right? Because imagine that, for example, among the women, basically the use of light would be very even, right? But you have many, many women, right? And for the man, it would be super distinct, right? But you have very, very few men, right? And now if you just added it up together, you'd say it's somewhere in between, right? But if you know that there's a lot more women in the data, you basically say, well, we only have, like, let's say 5 men. So we can't really generalize that. So we'll basically, we'll strengthen, we'll weigh the results of the women more than the men. Of course, we very few. So it's still yes, no, but now we take the frequency of the two groups into account, right? Okay, so here we actually see that we have a few more men in the data, right? So overall, it's not perfectly balanced, but it's pretty balanced, right? But now we have a Gini coefficient for gender. That's important. Remember, of course, we can split by age, gender, or status. These are the 3 splits that we can make in our data set, right? Okay, so we do exactly the same. Or here I actually did it in R just to show you. Again, you don't need to do this. We need to do exactly the same calculation, not for a gender, but we need to do it for age, and we need to do it for status, right? And now when we have the Gini coefficient here, so for gender, it's 0.46. For age is 0.43. And for status is 0.49, right? So because the Gini coefficient for age is the lowest, that tells the computer, okay, we split by age, right? So that's how it determines the first split, right? Okay, the next step then is we only look at the young speakers, right? Because we split by age. Now we only look at young speakers. And here we again calculate within this group, within the young speakers, is there an effect of gender and is there an effect of status? So we calculate the Gini coefficient again, just for the young group, right? And then we check which has the lower Gini coefficient, right? And then we split by that, right? And then for the last thing, right? So we have then, for example, age, then status, and then we'll check again for gender, right? And basically we'll split the data again. And if you have many more predictors, we'll do that until it basically has all variables considered, right? Okay. Yeah. You don't need to do any of that. Yes. It was just important for me because if you want to use this method, right, I thought it would actually be relevant for you to understand how does it work? Like, how does the computer determine when to split, right? And it's in this, traditionally it's based on Genie, right? You can also say you use another measure like chi-square or something like that, right? But for traditionally, it has always been Genie. Right. Now, I told you before, there's a difference between decision trees and conditional inference trees, right? So decision trees, you have all possible splits, right? For conditional inference trees, you only have significant splits. So what happens is that at each split, right, you'll, in addition to calculating Genie, you'll also do a chi-square test. And if the chi-square test is not significant, then you don't need to calculate Genie because then you'll say there will be no split. But if there's a significant difference, then basically you check, okay, which of the factors do we need to split by, right? That's why for conditional inference trees, you won't see all possible nodes, but just the nodes where there's a significant difference. All right. So this is essentially what we've done. We split by age, right? And then we get this data set for the young speakers that we then apply, calculate the Gini coefficient for, and you get the old data set and you get Gini coefficient for, and so on. And here I just did all the calculations, just so they can basically check whether what I'm talking about makes sense. Now, what I've talked about now is when you calculate the data, you can split it by male and female, right? But what about if you have numeric variables, right? So let's say you have frequencies, right? You can't tabulate frequencies, right? Because you don't know where to split it, right? So how a conditional inference tree works is that it looks at a speaker. For example, we have one speaker who's 15 and that speaker uses like, right? Speaker of 37 years of age doesn't use like. 63 doesn't use like. 42 uses like. 22 uses like. 27 uses like, right? So where does the computer determine where to split it, right? What's the difference between young and old now, right? So what happens is that it will also split the data, and it will do it like this, right? It will basically include the split between each of the ages. So first, we've ordered the age from low to high. So 15 is the lowest age, and then 63 is the oldest age, right? So we order the age groups, and then we put a split in between each of the speakers, right? And so what we can do now is we can calculate what's the Genie of this versus this, right? What's the Genie of these two versus these three? What's the Genie of these three versus these two, right? So it checks for all possible splits when you have a numeric variable, right? And then it will check, okay, what's the best option for splitting the numeric variable, right? So it's not only possible to do this for groups that you've predefined, but will also give you that for numeric variables, right? And the way that it does that is it basically splits the data, yeah? Yes, yeah. But basically when you have a numeric variable, it will check how can we arrive at a certain group, right? We'll test all possible groups, and then it will take the group which has the lowest Genie and split there, right? Just the way that we did for a male and female, where we knew the groups, it will basically check that for all different separations here, right? Just quick word. You might think that the best split would be if we take a speaker, just one, that definitely has users like, right? Of course, then, yeah, 100% certain. So the youngest age group will have the highest number of or probability of using like. The problem then is that Genie takes the frequency into account, right? And as I said before, if you've only very few people in the category, it will actually think, oh, it's only a single speaker. I don't take this seriously. They will arrive at groups that have a certain size. Below that, the Genie will by default be very low, right? Okay. Right. So here, this is exactly what I did. I calculated the Genie for all the different possible groups, right? And then you would see that the lowest Genie in this case is if we split here at 50 and a half years of age, right? That in this case, in this example, would give us a split, right? So younger than 52 and older than 52. I just used this to show you how it splits on numeric data. All right, cool. So now I've explained to you essentially what these trees are, that they split the data set, right? That's what they do. And the higher is split, the more important it is, so to say, right? And now I wanted to go over an example where I show you how you do this in R. R is a programming language that was developed out of statistical analyses. So when you look at statistics in the language sciences, but also the social sciences, R is the most frequent environment in which you do stats. You also might have heard of SPSS, right? That's also software that you use to basically do statistics, right? But people switch to R more and more. So essentially, you have like this cross pattern. Like when I was at university, most people were still using SPSS, right? And very few people used R, right? And now basically the number of R users has increased, right? Because it's free and open source, more flexible, and the number of SPSS users goes down. So here I want to show you how you can basically do this in R. So let me take a seat. Okay, so here the first I have two examples. One is on discourse like, just basically because now you're familiar with it, so it will be easier to for you to understand what we're doing. And then we have another example where we look at numeric data, which looks at prepositions. And then in the third step, we'll actually run the code. You'll run the code yourself. Okay, up to now, do you have any questions? Like, is it clear, more or less? You don't look convinced. If there's anything you'd like me to explain, just let me know. Yeah? All right. Okay. Right. So the first example here is on discourse-like, and basically it has 4 variables: whether a person is a like user, what the status of the person is, the gender, and the age, right? And if you want to load the data, you need to load the data into your computer, so to say, right? And you do not have the data on your computers, right? So basically, where do you get the data? So in this case, I uploaded it to the World Wide Web, and there it is, and you can download it. And so what this line of code does is it reads that data into your computer from the web. So that would only work if you have internet access. Without internet access, you can't download the data, right? And then the head function here, that gives you the first 6 rows of the data set. So it just shows you the first 6 rows, because imagine you have a data set that's 10,000 rows long. You don't want to see all the 10,000 rows, right? Because then you basically see lots and lots of rows and it wouldn't really help. So basically you load the data, you call it something, that you call it a name. In this case, I call it sit data. And then you use the head function to inspect the data, right? And then you basically get an overview of the data. Another option to look at the data. So here, cat gives us the first 6 rows. Another option is to use str, and that gives us the structure. So str stands for structure, the structure of the data. And here we see it's a data frame that consists out of 251 observations of 4 variables. Yeah. Yeah. So it really depends, all right? So I basically have R Studio on my computer, and typically I have the data sets in a folder somewhere, and then I load them from that folder into R, right? And if you want to know about how you can load data, I told you about the lab that I'm running in Australia, right? It's called the Ladau lab. And there we have tutorials on how to use R for linguists, essentially, but everybody in the humanities. When you go to tutorials, here you have something that's called R Basics. And there you basically have different tutorials on how to do stuff, right? And here, for example, you could use Get Started, which tells you how do I actually start using R? What should I do? And it will give you a step-by-step introduction on how you can do that. And the next tutorial then is already how to actually load data sets, right? Because you might have data in different formats, like in a CSV format or an Excel spreadsheet or a text file and so on, right? So there we wrote basically a tutorial on how you can load different types of data, right? Yeah, no worries at all, right? Okay, so in terms of structure, it tells us it's a data frame consisting out of 251 observations, so rows, and we have 4 columns, 4 variables, right? So the data set looks like I showed you before. I think, didn't we have it here somewhere? Here. So this is basically, if you would have a look at Excel, this is essentially what it would look like, right? Okay. Now, the next thing that we see here is that variables can have different types, right? They can be, for example, numbers, or they can be characters, or they can be factors. Now, what's the difference between characters and factors? When you write a word, right? Each instance of that word is a separate instance of that word, right? Whereas a factor understands that, oh, that's not a separate thing. That's actually the same thing, just another instance of it. Let's explain not optimally. But let's say if I look at age, right? And I see 15 to 40, 15 to 40, 15 to 40, 41 to 80. If it's a character, then all these are really separate things, right? Whereas if it's a factor, then I will understand, that's the same as that, and that's something different, right? So basically you need to tell R we're not dealing with characters here or with strings. And the way to do that is to use mutate if. So mutate means to change a variable. And here we need to change the character variables into a factor, right? Again, don't worry about it. I completely understand that that is new and you won't be able to implement that, right? But I need to explain to you the different steps that you need to go through when you do an analysis, right? So here we first load the data. We then check out what does it look like. We check the structure of the data. And here we would see, okay, characters, we can't really work with characters, so we need to mutate them and change them into factors. And now when we use structure again, now what we'll see is that H actually consists out of 2 levels, right? And for each of these levels, now we see that the first 3 instances belong to the first factor level, and then the next 4 instances belong to the second level, and so on, right? And the same for the other things, right? So this would be female, female, male, female, male, male, female, and so on, right? All right. So then what you can do is you can basically control for repeated measures, right? Now with each statistical test, if you do it, you have a chance of being wrong. And the chance of being wrong is exactly 5% for traditional reasons, right? So if you run thousands of tests and you have a likelihood of being wrong at 5%, then actually your chance of being wrong when you do thousands of tests becomes very, very high, right? So what you can do is you can actually lower your probability level so that something is only considered if you can be really, really sure that you're not making an error, right? To put it in prose, so to say, right? So you can actually adapt the threshold where you consider something significant, right? So if you do 1,000 tests, the threshold will no longer be 5%, but 5 divided by 1,000, because you run 1,000 tests. And so for something to be considered significant will then be much, much, much harder, right? But at the same time, that means that you can be very sure that you're not reporting a result that is wrong, right? Okay. And then we've loaded the data, we've converted characters into factors, we've basically checked for repeated measures, and then we run our tree, right? And what we do here is we use the C-tree function from the PartyKit package. And here what we have is we want to predict like user based on age, gender, and status. And those variables all come from the SIT data set, right? So, and we store the results in something that we called, we can also call it Hans or Georg, but in this case, we called it sitd.ctree, right? Which is just the results of the C-tree. And then we can plot this SIT C-tree, and we can adapt the font size, right? So how big something is. Now, what does plot mean? Plot just means visualize or create a figure, right? And font size means how big do you want this writing to be, right? So if you make the font bigger, you'll also get a bigger font here, like it will be more easily readable, right? Okay. So this is basically all the command that you need when you want to create a conditional inference tree, right? And then to visualize it, you just need to plot those results, right? And then you get this, right? Which you can then basically copy and put into your term paper or a publication. And when someone reads it, that person will understand, okay, when we look at like use, the most important factor is age. And then status plays a role, but only among young speakers. And gender plays a role, but only among old speakers, right? So that's basically how people can interpret that tree now. So that would mean load the data, you convert characters into factors, you set the controls, you run the tree, and you plot or visualize the results. That's basically the steps that you need to go through when you run an analysis like that, right? Okay. Do you have any questions so far? Okay, I know it's kind of boring, but but I just want to basically explain to you how it works and what steps you need to take, and also show you the code so that you basically see what we're going to execute later on, right? Okay. Now, in this example, as I said, we only deal with binary factors, right? And oftentimes we're actually not dealing with binary factors. We're dealing with other types of data, more complex data, right? So in the second example, we're looking at a data set that tells us how many prepositions per 1,000 words were in a text, right? In many different texts. So in this case, we are looking at all the texts that are part of the Penn corpus of historical English. And they contain private letters or legal texts or Bible translations or fiction or scientific texts. So all types of different texts, right? And so what I did was I just looked at how many prepositions are in each text, how many words does the text have? And that means that I could calculate per 1,000 words, how many prepositions does the text have, right? I checked whether it was written in the north of England or in the south of England. The genre, and basically the date when it was written, right? And here I could do the stuff for the entire data set, but I wanted to basically make the trees simpler for you to see, right? And so what I did was I reduced the genres to basically 5 genres. And I also reduced the date to be now only 5 date categories or so, right? From very old to 1913 or something. All right. So here what I did was, this should be familiar with, for you, right? So the first step always consists in loading the data, right? And again, I load it from the web. And then we have this symbol here, which can be translated as and then. So we load the data and then we mutate the characters into factors, right? And then, here again is an and then, I removed basically the original columns, which contain the exact date, the exact genre, and the name of the text. Because there are thousands of texts, I couldn't include that to split the data. And the result, what we see here is that we have prepositions, which is the relative frequency of prepositions. Then we have region, north and south. We have genre, which has 5 levels, and date, which also has 5 levels, right? Again, we set the controls, right? Again, we apply the C-tree function. We want to predict prepositions now by date, region, and genre. In this case, we use a data set that's called PVD. Here, this is where we call the data set PVD. And then we plot the results. And because I didn't want to override the initial tree, I called this sit C-tree 2, right? And now this is what we get. Now this looks different, right, from the first one. The first one basically gave us probabilities for yes and no, right? That's what the first tree did. Now the second basically deals with frequencies, and so it needs to display the results differently. Has anyone an idea how to interpret? Yeah. Yes. Do you know what is the median? Are you aware what a median is? It's a measure of the central tendency. So it's like the average, but the average would be calculated by summing up all values and then dividing by the number of values, right? And the median would be if you order all values, right? And then you take the value exactly in the middle, right? That would be the median. And the good thing about the median is it's not impacted by outliers as much as the mean is, because the mean is actually very much impacted by outliers. The median is not, right? Exactly. So that black line is the median, right, for that category. Now, do you remember what the box was? Yeah. Very good. Exactly. So exactly 50% of data points in this category, for example, would be within this box, right? And then you have these things which are called whiskers, right? And the whiskers extend 1.96 standard deviations from the median, right? Which is complex. So you would expect 95% of data points to be within the whisker. So this is the median, the central value. The box contains 50% of the data. And within the whiskers, you should have 95% of the data, right? And so what this means is that you have slightly different distributions, which tells us that if we split the data up in this way, we can make more informed guesses about the number of propositions in a text, right? So this is how we would split up the data set to arrive at maximally distinct distributions of the prepositions in those texts, right? Now, the first split here is by genre, and it tells us that here are legal text and non-fiction text, right? On the other side, we have conversational, fiction, and religious, right? Among legal and non-fiction, the next important factor is date, right? So genre, most important, then date. And here we have an earlier period, and here we have a later period, right? And in the earlier period, we actually have a lower mean frequency than here, right? You see that this box is higher than this, right? So that would tell us that basically for these two genres, right, the later texts have on average a higher frequency of prepositions in the earlier text, right? And for these, basically, we would then say, okay, this was already a great split for genre, right? But then it actually checked, genre is again the most important factor, right? So we need to split it down further. So have conversational and religious versus fiction, right? And within fiction, we again have an earlier and a later period. So earlier, later. Earlier, very low frequency of preposition. Later, a bit higher, right? And we have the exact same thing here. So here we also have date within conversational and religious. And here, basically, it doesn't really make a difference. There's actually a slightly higher percentage, higher frequency of prepositions in the newer text. Okay. So this is how you can interpret this, and this would be how you would basically implement that if you had a numeric dependent version. Yeah. Yeah, it will always split in two. So you can only have binary splits. If you have a three-way split, right, then it would have to split first and then split again, right? But you can't have three-way splits. It's not possible. It's only a binary decision. Yeah, it's always yes or no, right? So depending on where to go. Yes, we have a question by Hannah.
Yeah, so earlier you also said you split whether it was written in the south and north. Now it's not in this plot. Does it mean it just doesn't matter?
Yes, exactly. So
Okay.
that's super important, right? So that you didn't hear a question, right? So Hannah said that, well, earlier you said that also we have information on region, whether something was written in the north or in the south. But here in the splits, region does not figure. It's not there. So that means that region actually has no impact on prepositions in this data, right? So that tells us that something does not have a significant impact, right? So if there's no split by a variable, it's not relevant. You can ignore it, right? Right. Now, this is not really relevant for you, but because I know I made that stuff available and we'll go through it later, I wanted to show you how I can prettify or make nicer trees. Of course, this is okay, right? But there are actually ways in which you can make it prettier. The only problem there is that the code is super complex. So to make it nicer, actually you need all this chunk of code, which is a lot longer, but then you get a much nicer visualization, right? Where, yeah, I actually only did it for the first data set, right? But you'd have to adapt the code. And if you play around with it, you might actually be able to create a plot for your data and then basically have it in a format that is publishable, right? Like this type of publication or this figure is accepted by journals, but actually high quality journals, if you do it this way, right? Yeah, I just want to give you the code and show you how you can make it nicer, right? So that you might be able to adapt it. And what you would need to do is, if you have your own data, you'd basically need to check what's my dependent variable, because your dependent variable will probably not be like user, right? It will be something else. So you need to change like user to your dependent variable, right? And now you might say, well, I can't change it. It's actually fixed. Like if I type something, it doesn't do anything, right? Because this is really just a website, right? It's like, it's nothing that interacts with you. It's just a static site, right? So in order to fix this, we can go to the last section, which is the practice section, right? And what I'd like you to do now is to click on Launch Binder. And then what will happen, don't worry about this 404. It scared me too, but actually it still works. So what happens now is that somewhere in Los Alamos, computers will fire up and they will do the calculation for you. And the cool thing is that you can actually write in that document. And every time that you enter it, you can use it again, right? So it will always be able to use it. It just takes a little bit of time for it to fire up. Yes. Yeah. What do you mean specifically? Yeah. That's why I actually wrote this. So in this document, you are able to write and to change stuff and also upload your own data. And you can go back to this and I'll just leave it there. So even in 2 or 3 years, you'll be able to click on this button, the Binder instance will fire up, and then you'll be able to actually upload your own data and apply the analysis. The only thing you need to do is to change the names of the variables that you're interested in and the name of your data set. Yes, so again, if you go to Ladal, right? If you go to statistics, there are actually tutorials on descriptive statistics, like how you describe data sets, basic inferential statistics, regression analysis, and so on, right? So there are actually templates for more complex stuff. Let's go to basic inferential tests, right? So here, basically this, yeah, what it tells you is what you need to do if you want to do the analysis on your own computer, right? So if you want to use your own computer, then basically you need to install these packages, right? Because R is like a toolbox, but it only comes with a screwdriver. And if you want to do anything more complex, you need to add more tools to your toolbox. And these tools are called packages. And so you need to install packages to do other things, right? And yeah, so you install the package and then it allows you to do more complex stuff, right? And what we do here is we then load different types of data sets. Like here we see one data set where we have the number of words by gender, for example. And then it shows you how you can visualize the data and check assumptions. And also how you can do tests like, for example, a t-test, right? So t-test is something where when you have a numeric dependent variable and a binary predictor, then you'd use a t-test to see if there's a significant difference. And all the code that's here in Ladal, you can use it for your own analysis. So you can then basically copy the code and put it into your own notebook. Yeah. Almost there. Yes? Yeah. No. You can actually use it exactly like for SPSS. You have it on your computer and you upload it. The only thing is here, I wanted to do it in a way, if I had you install R and RStudio, right? It would be the first time for you to use it. And we'll basically have to fix problems with all of your computers before we can actually get to something, right? And one way to get around that is to fire up a virtual machine like I did here. And then basically everybody can run that code on a standardized computer. So we get around all the issues that arise when people use different softwares. I don't know whether you've ever done that, but when you download and use a software, typically some problems will pop up, right? It can be that you have different versions or something doesn't work on your computer, right? And by using a virtual machine, we get rid of all of that, right? So essentially, all of us use that virtual machine now. And here, just to give you an idea, I can actually go in there and I can type something, right? So you can actually change that code. You can also call things differently and still run that code, right? I just want to wait. Is everybody there? Like, does your stuff look like this? Yeah. Okay, so what I did here is I also pre-installed all the tools we need. So we don't need to install them. They're already there. The only thing is we need to take them out of the toolbox, right? And we do that by loading them from the library. So the first chunk here just means give me those tools, right? And activate them. And how do we do this? We just press the play button, right? So here we press the play button, and then you'll see a star, and you see some result. And then when you have a number, it tells you that that code chunk has been executed, right? So the first code chunk, but just loads basically the tools we need for this analysis. That's what the first code chunk does, right? That's basically how we prepare the session. So before you basically start building like a cupboard or something, you get the tools on your workbench. That's the first step. That's how you prepare, right? Now, in the second step, I wanted to show you how you can upload your own data. So remember, when I'm gone, right, you can still use that code and can actually upload your own data and use that, right? So how does it work? You have this folder symbol, and you see that folder symbol here, right? You see it? For the people who are at home, do you see what I'm doing with my cursor?
Yes.
Yeah. All right. So here we have the folder symbol. We can go to that folder. And here, then I tell you, you need to click on this symbol here, right? Which is there. And that will open up a browser. Now you can, for example, open your own data set. Here, for example, I wanted to load this data set. So I'm going to upload this data set. And now it's here, right? You see it now, that data set that I just clicked on is called test data 1. And now it's here on the left, yeah? And here, now that I've uploaded it to that virtual machine, now I can load it into that virtual machine using this code chunk, right? So now it's there, but it's not loaded into the program service, right? And so we execute this code chunk. How do we run this code chunk? What do we need to do?
Press play.
By the way, in your case, this won't work because you won't find this data set, right? Because it's not on your computer. When you go to our workshop folder, there's actually a subfolder that's called data. And there I put the test data in there, so you can actually download it if you like, but you don't have to, right? Now, if you have a test data loaded, then how do you run it? You just press the run button, and then it will execute this code chunk. And here it shows us that it has actually loaded that data set, right? Now you might have a different data set, right? That's called differently. So you can really just go to this folder symbol, go to upload, and take a spreadsheet, an Excel XX file from somewhere on your computer, right? Just from anywhere you like, right? And once you've done that, you can then change the name and then enter the name of the data set that you've uploaded, right? I don't know what your data set is called, which is why I just used my test data set. But you can upload your own Excel spreadsheet now, right? So you should be able, I don't know if you're trying this, but you should be able to upload your own Excel spreadsheet. How much time do we have? Because I think we don't have 20 minutes. That's fine. That'll work. I just want to give you some time to upload your own data in case you want. Has it worked? So when you've uploaded it, it should appear on this side somewhere. It does. Okay, then what you need to do is, what's the name of your data set? Like, how's it called? Then you would just write conference here, like that, right? And then you would hit the play button. Now, for me, it will throw an error because I have no data set here that's called conference. Do you understand why it will cause the error? So if I now run it, it will tell me error, there is no data set that's called conference, right? You just click in here. Like, do you have this open? Okay, so you were with the when you go to the repository, right? Did you have the website open? Yeah. Okay, if you go to practice, does it look like this now? Yes. So sorry for this. So if there's any difference between what the file is called here and the file name here, it won't find it. Like, the computer is really, really stupid, right? If there's any mistake, if it's a capitalization or anything, it won't recognize it, right? It will really check, is it exactly what I write there? And if you forget a number or a letter, it won't find it. Yes, everything. I think I call it test data. Yes. Yep. You will always explicitly don't have certain programs, right? So that can be a problem when you have tests in there. Try to avoid that, right? There was another question. Awesome. That's it. For the people online, I just want to wait until everybody is with us again, all right? No. Yeah. So here one. That's why it tells us there is no data. So this would have been times 100 worse if we all had our computers and would work on them. So these problems are still manageable. So there might be a problem if you call your sheet a certain name, right? That can also be a problem, right? Right, but I'll get back to you and I'll help you in a bit. I just want to basically, for the others, go ahead. In this case here, I use data from the web. And so I use a different command. Like if you check here, I use read XL as X, right? And here I said read delim, which stands for delimited file. Delimited means that each cell content is separated, delimited by something. And in my case, it's a tab stop, which is \t, which stands for tab stop. And so if I execute this bit, then you'll see that data that we talked about before. And then you can actually execute everything just by going to the code box and hitting the play button. Right? Right. So here I actually gave you additional information. So did it work or no? Perfect. Right. So that's kind of, yeah, that's kind of tricky, right? I have to deal with what you have, right? So that's why I used I used data set that I control myself in order to basically have it, yeah, avoidable for everybody. Now there's something that I wanted to show you, because here we define a control, right? And we did this before as well, but here there's no control, right? Now you can add the control by just copying this here, right? I'm just going to Control C. And I put a comma there, and then I add this. Now the problem is if I do this, actually it won't split. That's because when we determine what split to use, all right, actually when we use the chi-square test, it will tell us there's no significant difference. So we'll actually not split if we control for repeated measures, right? But because that looks stupid, and this is just a tutorial or a workshop, I took it out. So this means, oh, sorry. This means that actually we are not doing a perfect analysis. So we're not controlling for repeated measures. But I explained it here, what I'm doing, right? So if you return to this, you can actually implement it. Right, and now the next question is, well, I have this image, and I can probably copy it somehow, right? Using, I actually have no idea. So the way to do that is to just run this piece of code. And if you run that, you'll actually see that somewhere here, it will save an image. It saved an image before. No, it really does. Here, there, now. Where is it now? There. That's not what I wanted. But it saves it. I checked it. Before it saved it somewhere here and just appears later. I'll just save the image there as tree1. What's it now? It's disappeared. But that's basically how you save data then, all right? Yeah, you can, oh, sorry, I just here, I think it's on and off. Hello. I think I have to do with how I have the computer. There it is. Okay, I won't change it, but you can also call it differently, right? Everything here, you can basically write your own stuff in there, right? So that also means that here, when you upload your own data, right, you'll have to use different names for the variables, because in your data, of course, it won't find that variable, right? So it might be question 1 or whatever. Remember, avoid spaces, right? Because whenever there's a space, it will assume the next thing is something else, right? So if I had like space user, then it would consider there are 2 things. One is called like, and the other is called user. And it will tell me I don't find like, and I don't find user, right? So try to avoid spaces when you name stuff, right? Okay, now the second example, same thing, we load the data set. Here I use that pipe, and then I mutate right away. And I selected basically only the variables that I wanted. Here you can see now these are called factors. Double is another name for numeric variable. Here I then run this tree, and you get this tree. You can save it. And here you can prettify the tree, the first tree. Then you get this and the last one, right? And if you want to return to the GitHub repo, which contains all the materials, you just need to click on this, and it'll take you back to the GitHub repository, right? Okay, so just as a wrap up, right, while you're dabbling around, what we've done today, basically, I try to explain to you what tree-based methods are I told you about the advantages that they take any type of variable and any number of predictors, right? I explained to you how they work, that they split the data and that they split the data based on Genie coefficients, right? We learned how to calculate them. I told you about the disadvantages, that when the initial split is a conditional, like with a coffee, right? I really hate coffee, but when I have a cigarette, I love it, right? Then they don't work well, right? Then we went over the code, and now you basically have an interactive code book that you can use whenever you want, right? So even in a year, you can click this link, and basically the notebook will fire up. You can use it for your analysis, right? And also, you can just shoot me mail. My email is martin.schweinberger@uq.edu.au. How horrible, right? Would it be possible that could you send an email to everybody which lists that? That'd be great, right? So you can contact me later on if you have any questions, right? So I hope you learned something, right? I know that this is really challenging. I'm aware of this, right? It's really difficult because I'm in this mindset where I basically think about things and the world in terms of you have phenomena and outcomes and they're affected by something, right? And for someone who's not used to this kind of thinking, on this algorithmic kind of thinking, it's really difficult to wrap your head around what we're doing here, right? I completely get that. And also there are many concepts that I introduced today that are new, right? I am fully aware of that. I hope that if you can follow right now, that at least have a broad understanding, right? That you got something out of it, that it didn't like, that you don't think it's completely irrelevant to you, right? It might be, but you know, I try to basically explain to you how you can use this. And maybe for your term papers or BA or MA thesis, you basically see how you can use this in the future, right? So yeah, thank you very much for hosting me. It was very nice meeting you, everybody. You did fabulously well. There was no crying. I'm super happy about that, right? So yeah, and also apologies for the examples. There might not be the best examples. I'm trying my best to make something as plastic as possible, right? Yeah, I hope you got something out of it. And that was it for today's workshop on tree-based methods. Okay, everybody at home, just a quick question. Is there anything else you'd like to ask? Is there anything you'd like to say?
I was wondering about how I would have to prepare the data in the Excel spreadsheet.
Yeah. Okay, there's actually, Hannah asked a very, very good question, which is really relevant to you, right? So what you can see, or it all depends on the way that your data is structured in Excel, right? That's something that you need to understand, right? So what you need to prepare it in the way that you have basically column names, right? And then each cell has a specific value, right? So what you cannot have merged cells, for example, which we like to do when we have tables and want to summarize data. That does not work, right? So you have to really have each column has to have a separate name, right? Preferably without spaces, right? And try to have no cells with no values, right? But so it optimally should really look like this, right? And then it won't have, you won't have any problems. Yeah. So it really depends on, yeah, that you have separate columns, preferably short names without spaces, and yeah, just tidy data, and then it should work.
Perfect, thank you.
No worries, but that's super important, really. Yeah. 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 You don't have to. The computer does it for you. That's why. No, it's no, I get that, right? So essentially what we did here is I only showed you how to calculate the Genie coefficient so you know, right? You don't need to do this. All you need to do is you upload your data. Yes, right? So here you see that it calculated that, right? Because it has a tree, otherwise it couldn't arrive at a tree, right? And so it basically shows you the end result, right? And so there's nothing else you need to do. So all you need is really the interactive spreadsheet, and that's all you need for the analysis. Yeah. You do it on your own computer. Let's talk about this now, but separately, because if you do it on your computer, there's actually some things you need to change. Yeah. All right. If it's deleted, it's deleted. But next time, but like if you delete something here, I hope it doesn't matter. Please don't delete anything. I think it should be fine. So what happens after 10 minutes, basically you'll be thrown out, right? Because then the virtual machine will say you're no longer using me, right? And it costs basically money to run that machine. So if you open it next time, it should all be there in exactly this state. So it should be exactly like we opened it for the first time. And then if you want to do it again, you need to upload your data again. You need to include your code again. And then if you don't use it, it will shut down. And next time it will be like brand new, like reborn, but as an infant, right? Without anything you had done to it. So that should be fine. No trauma. Right. No worries at all. Right. Bye, everybody.